So we're at this point, I'm going to record it. You can go back and you can view the recording and review things, and it'll be posted wherever we need to post it. So most of us are here. It looks like we've got 10. We need to be having 12, but maybe the other ones will pop in again in a minute. And as I mentioned a moment ago, the default on these, when I created the meeting, all the users except for myself are set up as mute. But if you want to speak, just hold down your space bar on your computer and it will take your mute off. If you want to take your mute off and you're in a quiet background, that's fine. I'm just trying to avoid the barking dog in the neighborhood or the kid running through the house or whatever may be going on, and try to keep it as streamlined as possible. So before we start with working the end of chapter problems, and I'll share my screen and it'll be just like you're looking at a smartboard type environment. Anybody have any questions about how things are going to proceed, what we're going to do?
How are we doing like the pre-lab? Is that submitted or is that just submitted at the end with our actual?
That's a great question. It'll all be part of one report that you'll submit as a Word document. So you won't send me anything to approve. You're just going to, after we did the pre-lab today, over the process of tomorrow, I'm creating a video. I've already got most of it made, but I'm actually doing the experiment with I got a GoPro camera, but had no idea how to use it. And I'm learning how to use it with a headset. And I'm creating the data, and I'm going through and I'm telling you, this is this data point. You're going to have to watch the video to get all the points out of it and create your data table and do the conversion of the lab. That's the only way that I can try to make it as realistically as possible, because I can't bring you in the lab environment. But you'll just submit one Word document at the end. So, and the thing I'll tell you, if you want to have graphics, or if you want to take a picture of a table or something, just use your phone, take a picture of a table, and copy and as an image file and edit and paste that into a Word document. I'm sure all of you are capable of doing that, but that's a standard thing that we do with the online classes that I teach. You can, same thing if you write out an equation for something, just take an image of it and drop the image in your document. So don't, using equation editor is a neat thing to do. If you want to make something that looks fancy, but it takes a lot of effort to build equations in equation editor, and especially if you're like solving a problem or doing calculations. Just write it on a piece of scrap paper and take a picture and submit it. Any other questions? Okay, I think most of us have made it in. So at this point, I'm going to go ahead and do a screen share and swap over so that we're looking at the problems for the end of chapter 16. So we're going to, I moved the due date back, and I put an email out about that, or announcement out about that, about the chapter, the 16 assignment. Things are going to, we lost a week basically in our courses, so we're going to have to progress as far as we can, and cover as much detail as we can in the course, and wherever we're going to get it to is where we're going to get to. I don't know that we could either try to push super hard and get through all 20 chapters, which was the goal, or maybe we won't, but we're going to figure out where we're going to get. So with that, we're going to start looking at the end of chapter problems. You've got some mastering chemistry problems that are much like this. The first question is problem number 34. It says, identify each substance as an acid or as a base. Write the chemical equation showing it acting as an acid or base in aqueous solution according to the Arrhenius definition. So the Arrhenius definition is something as an acid is a proton donor, emits a proton off. And then a base is something that emits a hydroxide. So if we were to look at NaOH acting as a base, it would release the OH minus when it separates out as an ionic compound. You've got a metal and a polyatomic ion. So this is an example of something that's acting as a base, B for base. If we look at the next one, H2SO4, this is one of the ones I told you you would need to know the nature of. That's sulfuric acid. That's a common acid. So sulfuric acid actually has 2 protons that could come off. So it loses the first proton and it forms the HSO4 minus. That's called the bisulfate ion. And then as a secondary step, the bisulfate can lose a proton off and form the sulfate ion, the SO4 2 minus. So because there are 2 protons that can be donated, we call that one a diprotic acid. All right. The next one, HBr. Some of these in the formulas, it's pretty obvious what's happening. There's only a proton there, so this one is an acid. So it dissociates into the H plus and the Br minus. And then last one, again, it's pretty obvious as well. So strontium hydroxide dissociates into the strontium 2 plus cation, but because of the 2 here, it makes 2 hydroxide ions. So it would be an example of a dihydroxyl base. Okay, so that one's just identifying what the substance is as an acid or a base and writing the dissociation reaction. So problem 36 is looking at the different definition. That's the Bronsted-Lowry. So with the Bronsted-Lowry definition, we need to identify who is the acid and the base, as well as the conjugate acid bases in the system. So if we look at this first one on A, it's HI plus water yields H3O plus I minus. So if we look at the thing that goes from one form to the other, and we look at, is it the Bronsted-Lowry definition of an acid is a proton donor, and a base is a proton acceptor. So we just need to look at who loses the proton and who accepts a proton. And then on the opposite side, it forms the conjugates. So going from HI to I minus, it does that by losing a proton off. And then going from water to H3O plus, it does that by gaining the proton on. So based on that, we can make our simple definitions. So that means that this is the acid, and what it forms is the conjugate base. And this was the proton acceptor, so that means it's the base, and what it forms is the conjugate acid. So that's the conjugate acid-base pair system that we have for Bronsted-Lowry's. Anybody have a question on that one? All right. Okay, let's look at the next one. So on our next system, we've got the carbonate going to bicarbonate, and it's doing that by picking up a proton. So the fact that it's picking up a proton tells me that it is the acceptor. So that means it's the base in the system. So that instantly tells me this is going to be the conjugate acid in the system. So if I look at what happens in the other half of it, I've got water goes to the hydroxide. So it does that by losing the proton off. So the thing that loses the proton is working as the acid, and on the other side, it's working as the conjugate base. And just on the comparison of these two, I just want to reemphasize, so depending on what something's coupled to is going to depend on the way that it acts. In one case, water works as the base. On the other side, water works as the acid in the system. And I don't know why I put a C for acid, but it's working as a base in the bottom, and in the top up here, sorry, it's working as an acid in the bottom, a proton donor, and it's working as a base, the proton acceptor in the top. Okay, so let me shut my door. The dog pushed the door open. All right, let's go to the next problem. So problem 38, and you've got some mastering chemistry problems like these, are to write the conjugates for these pairs. And so on this case, it wants you to write the conjugate acid. So the conjugate acid would be when the base accepts a proton and it would form the conjugate acid on the right-hand side of the equation. So a base plus a proton, and it makes the conjugate acid. All right, so if we look at the first one, NH3, I just can't make an N there. I'll go ahead and fix that. Plus a proton, and it forms the NH4 plus. That's the conjugate acid in the system. All right, so go to the next one. I've got the ClO4 minus, that's the chlorate ion, and I add the proton to it, and it forms the ClO4 with the H in front of it. So that's perchloric acid, and perchloric acid is one of the ones that is a strong acid. So even though this is the formula for the conjugate acid, this would never happen, because the dissociation for a strong acid is always going to go in the direction where it disassociates, not associates back together. So that one's, it's the example that's in the book, but it's not necessarily, I think, a good example. All right, if we look at the sulfuric acid, and this system is bisulfate, picks up a proton, and it would form the H2SO4, so which is sulfuric acid. And again, that is a strong acid. So that would be one where this wouldn't happen. The equilibrium or the direction would only go in the form of disassociation. So I'm not sure why the authors put those couple in there, but I want you to understand that in the real world, those wouldn't happen. The next one would. Carbonate, CO3 minus, can pick up a proton and become bicarbonate. So there it would be as a conjugate acid. And that can actually go a second step. So the step beyond that is that the bicarbonate could pick up a proton and it could become fully protonated carbonic acid. So on each of these cases, this is a conjugate acid, and this is a conjugate acid as well. All right, so any questions on writing acid-base pairs? All right, so going to question 40. So it says that bicarbonate and hydrogen sulfide are amphoteric. Write an equation to show how each substance can act as an acid or base. So amphoteric means something that's capable of working as an acid or a base. And just like we showed that water could be a proton acceptor or a proton donor just a moment ago, these are compounds that have similar behavior. So if we look at the bicarbonate ion, and if we'll look at it acting as an acid first, so as an acid, it would be a proton donor. So it would lose its proton off and to become the carbonate ion. But also it could be a proton acceptor. So it could pick the proton up and it becomes the carbonic acid, the fully protonated. So here in this form, it's working as an acid. In this form, it's working as the base, and they're the same species. It just depends on what's present in the system. Is there something that needs to absorb protons, or is it needed to take protons? And that's one of the reasons that if you want to keep something around your household or even in the labs to try to neutralize acids or bases, one of the most common things that we keep in bulk is this guy, baking soda, sodium bicarbonate. And sodium bicarbonate, if you have a spill of acid or base, you can put it on there and it'll work to neutralize either one. So it's a great compound that to have around. Keep a bottle or a box of Arm & Hammer baking soda. If you spill something in the fridge, you'll absorb the odors out of it pretty well. But just to neutralize things, good old baking soda is a great reagent. That's a household agent that's easily obtained. Right, if we look at comparison, the one below, so if we look at the bisulfide could act as an acid by releasing this proton off to form the sulfide 2-. Remember, it's in the 6A family, so it's a 2- or ion, it's not a polyatomic ion. And then working again as a on the other form, working as a base, being a proton acceptor. They could pick the proton up and make the hydrogen sulfide. So hydrogen sulfide is one of the few that, even though this is an acid, we typically don't use the term acid in this one, but it's a pretty weak acid as acids go. All right, so let's look at, we only have a couple more of these to do. So number 42 is classify each of the following as a strong or weak, and then write the expression of the ionization constant. So let's take a look at that. I'm gonna see if I can move that to the other side. Get it out of the way. Yeah, here we go. Okay, so the first one, if we look at these groups of compounds, first question we have, is it a strong or is it a weak? And that's kind of something we have to know that from memory, going back what they are on the tables. HF is an example of a weak acid. HCHO2 is formic acid. It is also a weak acid. This is the stuff that was in ant bites. I talked about that in the video I posted Monday. Sulfuric acid, the loss of the first proton is a strong acid. The loss of the second proton is a weak acid. And carbonic acid, the one at the bottom, is an example of a weak acid. So when we write the Ka expressions, the Ka expressions are the weak acid that loses the proton off, and it forms the conjugate base. And if we write the Ka, the Kas will be products over reactants. So the products, equilibrium concentration in molarity, divided by the concentration of the reactants, which will be the protonated form of the acid. All right, so let's do a couple of these. So the protonated form goes on the left. It loses the proton off to form the conjugate base. And we would call this one the formate ion. And again, products over reactants. Okay. Now, one of the things that we talked about, and let me pick on the next one to illustrate that, is that the H plus doesn't exist if it's an aqueous solution. So I'm going to use that one as illustrate for C. So what happens if I have sulfuric acid, H2SO4, and it is placed in an aqueous solution? It dissociates 100% to form the bisulfate ion, and it forms the hydronium ion, H3O+. And this arrow is one directional. It's 100% to the right. So it's not a two-way equilibrium. So with this one, there's we just write that it's strong. We don't put a Ka expression. It's just completely to the right. But on the weak acid component of it, the loss of the second proton. So if the bisulfate in an aqueous solution reacts with water, so this one is a weak acid, it would form the sulfate ion, SO42 minus, plus the hydronium ion. Now, when we write the Ka expression for that, the Ka is products over reactants. So products are the sulfate ion, the hydronium, and the reactants are the bisulfate. All right. What about if I put, if water's the solvent in this, would water show up in this Ka expression? That's a question for y'all. Somebody tell me what you think.
It's a liquid, so it's not going to show up in it.
That's correct. The fact that it's a pure liquid in the system, its concentration doesn't show up the same way if it were anything that's a pure liquid or a solid, doesn't show up in our K expressions. So those doesn't appear. That's the reason we don't put it in here. So it doesn't matter really if I write it as this form or if I write it as the H plus, as I did in the ones above. So the fact that that proton is free or that proton is absorbed to a water molecule makes no difference. So that's the reason we said, I told you all a little earlier that you could use the H plus versus the hydronium H3O plus interchangeably. Those two things were equivalent in a water aqueous solutions, and they absolutely are. So you can interchange one for the other, and the same's true in the Ka expression. The water doesn't appear. Okay. All right, let me go ahead and do the last one right quick. So the last one in this series is the carbonic acid. So we'll do D down at the bottom. So looking at carbonic acid, so this one can lose a couple of protons off. So it loses the first proton, and it forms the bicarbonate ion. And if I write the Ka expression, and the fact that this one has two protons that can be lost, I'm going to go ahead and write the second one out. The bicarbonate can lose a proton, and it can form the carbonic acid. We call the first loss of the first proton Ka1, the loss of the second proton Ka2. So for the first proton, Ka1 would be H plus times the carbonate products over reactants. And then for the Ka2, again, products over reactants. Okay. All right, so question on that.
For those Ka expressions, would you like us to put each step or just the final one?
Now, the only thing that, if it asks for the Ka expression, so let me go to my highlighter here. So if it asks for the expression is this thing. So that's the Ka expression. If I ask you to write out the equilibria, that's what's on the left-hand side.
Like on the bottom in red, you have Ka1 and Ka2. Would you like us to put both of those steps?
If it's a diprotic acid, okay, I understand what you're asking now. If it's a diprotic or a polyprotic, yes, you need to show each ionization step. So we're going to talk about things that that can only lose one proton. In fact, I introduced that at the end of the last video that I did for Monday. So you have monoprotic acids that can lose just one, diprotics that can lose two, like carbonic acid here or sulfuric acid above it. And then you have some things that can lose three protons, like phosphoric acid is the common example we use in general chemistry. But in nature, there are things that can lose many more protons. There are some species, especially when you start looking at things like as large as a protein that is have molar masses maybe in the 100,000 range, they could possibly lose up to 20 or 30, and even cases 40 different protons off. In the same way, in the base form, they could absorb that many protons. So when you look at these large macromolecules, it becomes a much more complex system, but we stick with simple stuff in Gen Chem. Okay. All right, so going to problem 44, it's a little bit more complex problem. Let's just talk about how to approach it. So this is one of the things that I was introducing at the end of the last lecture, was that when you have weak acids, they can vary in their strength. So I copied this table 16.5 out of the notes and out of the textbook that list these acids in order based on what their pKa values are. So it says to rank in order of decreasing H3O plus or hydronium ion concentration, and then you've got 0.1 molar of all these different species. So what we need to know first are what are the strong acids versus what are the weak acids. And then once we know what's the strongs would be first. Okay, so if we look at HCl, HCl is a strong acid. If I look at HF, HF is a weak acid. HOCl is a weak acid as well. It's hypochlorous. So weak acid, and this is phenol. Phenol is a weak acid as well. So the one that's going to be, we want to go from strongest to weakest. And when I say that, what we want is the decreasing amount of the H3O plus. So when an acid works or performs its action, it releases the proton off. And the more forward that arrow is, or the stronger, that means it yields more amount of proton release. So the stronger the acid is, that means the more of the H plus or the hydronium ion is released. Well, the strongest one in this system is the strong acid. So it's going to be first. So this is the strongest is going to be the HCl. I don't need to put brackets around it. It's just going to be HCl. But then beyond that, we've got all these weak acids, and the weak acids ionization is going to depend on what this value is for Ka. I hope you can see that in your video. If not, go to table 16.5 and look at the reference on this. So this is table 16.5. All right, so what the Ka is a measure of that equilibrium constant that we wrote on the previous page. And if we remember, the larger the value of Ka, that means the more the equilibrium shifts in the forward direction. So even though for these weak acids, they're all numbers that are relatively small. They're to the negative power. They vary from like 10 to the minus 2 down to 10 to the minus 10th. So something that's 10 to the minus 2 is going to go forwards in the more than something that's 10 to the minus 4, which will go forwards something that's more than 10 to the minus 5th, and so going down the table. So the larger this number, the stronger the weak acid is. The stronger the weak acid, if it's equal concentrations of the weak acid, and these are all exactly 1/10 molar, that means that there would be more proton release. So we need to arrange all of these others based on what the value of the Ka is. So the ones that we have to choose from, so we've got hydrofluoric acid. So this is one of them. So here it is, it's Ka. So it's 6.8 times 10 to the minus 4th. And the next is the hypochlorous. Hypochlorous is here, and it's 10 to the minus 8th. And then finally, the last one is phenol. So this is phenol, and it is 10 to the minus 10th. So if I just go down the table and put them in order, they actually stack up in the way that they are listed in that table. So it would go HF would be the next strongest, and then the one that had even less hydronium ion would be the hypochlorous. And then finally, the one at the bottom would be the phenol. Okay, so to answer this one, we have to have some knowledge about the strengths of the weak acids. Now, if there were multiple strongs, let's say that there were HCl, 0.1 molar HCl, and 0.1 molar nitric acid. Both of those would 100% dissociate to produce the H plus and the conjugate base. On those cases, it would be equal amounts. So if that would have been the case, it would have been the two of those, it would have been equal for the nitric acid. So those two would have been equal. When you have strong acids, as soon as you put a strong acid in water, it completely dissociates to the H plus. So if they're the same concentration, it doesn't matter where the source of the proton came from. It's just that amount of proton in water. But when you have these weak acids that can partially ionize, that's where we have to look at a comparison of strength. So how much of it dissociates, or how far does that reaction go in the forward direction? And that's actually the topic of the notes as we're going forward, is to make those comparisons. Okay, so the last problem we're going to do today in these is problem 46. It says pick the stronger base from each of the following pair. And to do that, we actually have to go back and look at a comparison for some of these, and we're going to use the table that's on the previous page. So let's see, can I see how easy it is or difficult it is to copy that table? I think I can get that pretty easy. And we'll just pull the table here instead of going back and forth. Okay, so the first one that it's looking at is looking at this comparison of ClO4 minus and the ClO2 minus. And on this one, it wants to know which is the stronger base. Okay, so here's where we have to think about the table that that I showed you, where we went over and compared the strengths of the acids and bases. So I said you went from strong acids, and then you went down weaker and weaker to the weaker acids at the bottom. And then of the conjugate that was on the other side, that formed the weakest bases. And as you went further and further down, its conjugate would form a stronger base. So the base strength increase as you go down here. And then the converse of that was true for the acids. The acid strength was higher on this side, so acid strength. So when we look at this comparison, we need to look at, in terms of the base, what is the strength of the acid? So if I look at something, we think about these in terms of strength of the acids. So if I look at this one, its conjugate is a strong acid, and this one's conjugate is a weak acid. And that one's kind of, I think, an unfair comparison because it didn't make the short list in the table. Yeah, it is. So it's the top one in here. So it's a strong weak acid, but it's still, it would be like, it's maybe right here where the HClO4 is definitely a strong acid. Here would be the chlorous acid. It would be falling in here somewhere. So that means when I go to the base side, which is what we have on these, pick the stronger the base, this is going to be the weakest base over here. And as we go down the table, we get stronger. So that would make this one stronger in the pair. All right. So if I compare the next grouping, so it's the chloride ion. So the chloride is the conjugate to a strong acid. So it's the conjugate to hydrochloric acid, HCl, versus water. Now, water is amphoteric, so it means that water can be a proton donor or a proton acceptor. So it can pick up a proton and form the H3O plus, or it can lose a proton off and it can form the hydroxide. It can go either way. But if we look at what happens with HCl, HCl is an example of a strong acid, and strong acids form the weakest bases. So strong acids, the base has actually no strength at all, where water, though, has some strength working as a base. So on that, it would make water the strongest of this pair. Now, the last two is the tougher of the mixture, because we have to actually look at a comparison of these. Both of these, if we looked at the conjugate, so hydrogen cyanide and the hypochlorous acid, both are examples of weak acids. So WA, weak acid, weak acid. So what we need to figure out is which one is the stronger of the weak acids and which one is the weaker. So if I look at hypochlorous acid, so its value is 2.9 times 10 to the minus 8. And if I look at hydrocyanic acid, also called hydrogen cyanide, it's 4.9 times 10 to the minus 10th. So if I look at the bottom of the list, the HCN would be down here at the bottom and a little higher up. The HClO would be higher up. So going to the conjugates to the other side, the one that's further down is going to be the strongest. So that would make this guy, the HCN, the stronger of that pair. And those are pretty tricky problems to work if you can, and you'll see a few problems on the test that are going to be problems like that, where you're going to be given a group of ions that are conjugate bases, and you have to go comparison to the strength of the acids. But if you can just spend a little time, go back and look at the notes, look at the table that was in the notes, and understand how to make this relationship, you can work those problems pretty easily once you understand that they're coupled together as pairs, and what's a strong acid is a weak conjugate base. What's a weak acid is a strong conjugate base. They're opposites in the systems. All right. So with that, that's the end of the problems that I have based on the material that I've covered so far. Now the difficulty that I have is posting this in multiple videos. So I'm gonna to pause this for a moment. So